most systems, it simply ignores it and lets the request go to memory, and memory supplies the data. If this processor, if there are three operations that I'm going to mention here, I'm going to call this read shared, read for ownership, which I'll call RFO, and invalidate, or sometimes called upgrade. So read shared means, it's obvious what it means, I think. I want to be able to read a copy of other caches have it. I can't write it because that would cause an inconsistency, but I have a copy that I can read without having to go anyplace else. So if I have a variable that's widely shared, I'd like maybe every CPU to have a copy locally, and they can all read it out of their cache and run at cache speeds. Now, if any one of them wants to write it, what it needs to do now is to make sure that all the other copies are invalidated, and remember that its cache is the only copy. So in exchange for being able to write quickly to the cache, it has the responsibility of remembering I have the only valid copy. So if somebody else now who doesn't have the cache line, because I make sure they don't, if they want to get a copy of that, they send a request out, and I have to respond and say, memory doesn't have a copy of this, here's the data, and supply the data to the other cache. And furthermore, I write it back to memory probably, because I need to remember, I need memory to be able to respond in the future since it's now shared. So there's this protocol that involves snooping on the bus, which says every time a request goes out of the bus, you have to look at the address being requested and check to see if your cache has a copy. And if it does, you need to do the right thing, which is to say if you've got the only copy and it's modified, then you have to supply it. In the case of invalidate, the idea here is that you've got a copy in here, and this guy is saying, I've got a copy too, and I want to write it, and I currently only have a readable copy, in which case you simply have to invalidate your copy. So the whole protocol depends on this notion that there's a global medium for communicating, and you broadcast information, and in some cases get a response back, or at least an acknowledgement. Okay, so a transaction involves sometimes three separate elements, and that this node is saying, I want to do something. This node may or may not respond. If it doesn't respond, then memory simply responds by supplying the data. If this one does respond, then it's because, for example, it has the modified copy and must not allow memory to receive it. So we have a very complicated transaction. Notice that there may be three separate parties involved in what you would expect to be normally a simple transaction. You've got a node that's making a request. You don't even know who's going to respond, because if nobody else does, memory will respond, but any of the other nodes may respond. I wish I knew how to take a better guess. Okay, so notice that this bus has additional capabilities that a point-to-point interconnect doesn't have. It's depending on this property of broadcasting. Well, now it's long been known that the buses have certain limitations. Notice if you make this bus longer and add a lot more processors, you have to split the available total bandwidth among the processors, because if each processor generates a certain number of requests per unit of time, the more processors there are, the less each one can get, because there's a total limit on the bus. So somehow we have to divide up the bandwidth, and we can't expand it. So there's obviously a limit on